So in order to model radioactive decay, we're going to pretend that this jar right here, full of 128 pennies, is our newly formed igneous rock. So we have 128 pennies. The pennies inside are going to represent uranium molecules. So what I'm going to do is I'm going to shake it up, dump them out, and you're going to separate heads and tails. So we want to separate heads and tails. We're going to say that heads is our uranium and tails are our pennies that have decayed into lead. Okay, so I've separated my first pile into heads and tails. Again, heads represents the uranium that's left over. Tails represents the uranium that's decayed into lead. So that is now stable. My tails pile is now stable. So we're going to be counting the heads. So I already counted mine. I had 68 heads. So unchanged at isotopes. I would expect, because again, this is half-life, I would expect 64. So you can fill in this table. The expected is going to always be half of the previous number. So 64, 32, 16, 8, 4, 2, 1, and then 0. So that's what I would expect if I had, a perfect 50%, 50-50 decay. But I actually had 68. So what you're going to do is you're going to fill out the bottom of this table. You're going to have to keep doing runs until you run out of heads, basically. So all of my tails are going away. And I'm going to refill my pennies, my penny jar with just the heads and run this experiment again. So again, just the 68 pennies that I have left. I'm going to shake them again. I'm going to separate that into heads and tails, and I'm going to continue this procedure until I run out of heads. Okay, so this is how my data turned out after running 9 rounds of trials. Your data is obviously going to look just a little bit different, but we're going to take this data and put it into graphical analysis. So if I go into graphical analysis, new experiment, manual entry, you're able to actually manually input data in graphical analysis. So what we're going to do, if you click the dots right next to the 2 parameters, this one first, we'll do column option. This first column we're going to call time. Unit, it's going to seem a little weird, but we're going to call it half-life, because each round of trials we did represented 1 half-life. Second column, we're going to call actual. So these are going to be the actual values of the heads that we got. So I'm going to just name the unit heads. And if I go over to this right set of dots again, I can add a manual column. We're going to call this expected. And the units again are going to be heads. So I can pull over my data from Notability. And what I'm going to have you do right now is manually enter all of your data. So once I'm done with this, I can actually view it as a graph. So I'll go view one graph. And I want to make sure that I check my expected. So you should have actual, expected. Don't check time. So actual, expected are checked. And this is showing our decay curve for our radioactive decay. A couple little things. If I click the bottom button, we are going to apply a curve fit. And I'm going to go to natural exponent. So you can play around with the curve fit, find the one that looks the best, that kind of fits the data the best. A couple other things I can do here. If I switch to graphical options, I'm going to do points and lines. So good. This graph looks awesome. I'm going to full screen this again and take a screenshot. And this is the data that's going to go into our lab write-up. All right, so real quick here, I'm going to go over maybe a column or two of this last table. If you want to work on this on your own, fantastic. And you can turn the video off because this is all we're going to be doing. If you want a little help on how to fill out this column, that's what I'm going to do right now. So we started with 128 uranium isotopes. So we had 128 uranium isotopes. And we're going to write down our expected decay values for this first row. 64, 32, 16, 8, and 4. I'm just going to have you go down to 5 rounds, basically. And this is your expected values. Our number of lead atoms. So if we started with 128, went down to 64, we'll do 128 minus 64. That's going to equal 64. So we have 64 uranium atoms, 64 lead atoms. That makes sense because this is actually our first half-life. That ratio is 64 to 64. So the the ratio of uranium to the ratio of lead is 64 to 64, or another way to say that would be 1 to 1. So we have a 1-to-1 ratio. As I said, the number of half-lives, this is the first half-life. And an actual half-life of the decay of uranium to lead is 0.7 billion years. So if we go on, we now have 64 uranium atoms remaining. We decay down to 32. So if I started with 128, I'll minus 32. That means we have 96. At this point, we have 96 lead atoms. So 96 lead, 32 uranium. So the ratio for this one would be 32 to 96. And that's a 1 to 3 ratio. So it's the numbers are not going to go up, steadily. We went from a 1-to-1 ratio to a 1 to 3 ratio. So this ratio would be 1 to 3. This is our second half-life. And time, if the first one was 0.7 billion, we'll times that by 2. And that'll be 1.4 billion years old. So this is how we age igneous rocks. So those igneous rocks formations all the way back to part 1, those igneous intrusions, this is how we get the ages of those. So we can actually get good ages of igneous rocks using radiometric dating. So in the first part of this lab, we utilized radiometric decay analysis in order to determine the age of a rock unit or rock units in an outcrop. Now, unfortunately, radiometric analysis works really well, but only for one rock type, igneous rocks. So those are our magma rock formations. Now, if you refer to the sheet on the page before, if you had read through that with your group, you know that there are 3 major rock units: igneous, sedimentary, and metamorphic. Sedimentary rocks and metamorphic rocks, we are not able to use radiometric analysis in order to determine the age of these units.
So if we're not able to find the exact ages of sedimentary and metamorphic rock units, how is it that geologists can be so confident in estimating the timescales of various rock formations, including the metamorphic and sedimentary rocks? The technique that geologists utilize in order to find this is called relative aging. So using the absolute ages from our radiometric analysis of igneous rocks in the area, we're able to put time constraints on the formation of sedimentary and metamorphic rocks. So what I've done now is given you 3 ages of the 3 igneous rock formations that we have in this lab. So we have our granite, which is 1.7 billion years old. We have our pegmatite, which is 1 billion years old. And we have our basalt, which is 250 million years old. Million, not billion. So the basalt is definitely the youngest layer out of these 3. So we can find the exact age of these 3 rock units using radiometric analysis, just like we did in the first part. For the purpose of this experiment, what we're going to do is assume that we know these ages, the ones that I just gave you, and we're going to determine the relative ages of the 3 fossils in this rock sequence. So the bacteria fossil that's buried inside the slate, the trilobite fossil that's buried inside the limestone, and the triceratops fossil, which is inside the shale and siltstone layer above the volcanic ash. So we're going to be able to find rough estimates, time constraints, of the ages of these fossils. So even though we can't find an age of the slate, we can't find an age of the limestone, and we can't find an age of the shale and siltstone layer, we are going to be able to get pretty good time constraints on all of these sequences. So the first thing that we have to do to figure this out is we have to determine the relative ages of all of the units. So for example, the slate here at the bottom is the bottommost layer. The only one that might be kind of confusing when you're looking at the slate and the age of the slate is this granite intrusion. But we should know, using the principle of cross-cutting relationships that we talked about in our chapter, if the granite is cutting through the slate, then the granite is going to be younger than the slate. So given that the slate is 1, the bottommost layer, and 2, the granite intrusion that is probably the next closest is cutting through the slate, we know that the slate is the oldest rock, and the granite is the next oldest. So here's the deal. We can actually figure out the first fossil range of this bacteria fossil. So we have our bacteria fossil here. If the slate is older than the granite, then the bacteria fossil is going to be older than 1.7 billion years. So actually, that is part of the answer for number 1 on the page below. The slate fossil, the fossil inside the slate, sorry, is older than 1.7 billion years. And then I do ask you, well, why can't we find the age of that specific rock unit? So you got to make sure that you answer both parts. So for the first part of that question, the slate is older than 1.7 billion years old, so that means the bacteria fossil is older than 1.7 billion years old. Sometimes you can do better with a range. You can give me a lower bounds and an upper bounds. In this case, all we can say about that slate layer is that it is older than 1.7 billion. And then why can't we find the age of that rock? Well, it's because it's a metamorphic rock. So what I would do with your group is look at the page above where I give you a little bit of a field guide walkthrough on the different rock units. And I want you to come up with a good answer as to why you're not able to find the exact age of the metamorphic rock slate. And so that's kind of how you're going to answer the questions on this part of the lab. So I gave you 2 of the underlying rock layer ages here, relative ages, the slate and the granite. So you're going to start from there. You're going to fill out the rest of this sheet. And then you should be able to finish answering question 1 on the page below, and then move on to question 2, which talks about the trilobite fossil. Limestone is a sedimentary rock, so that's going to be, you're going to have a different explanation for as to why you can't find an age of that. And then the triceratops fossil. All right, this was our Ages of Rock slab. Thanks for watching, and let me know if you have any questions.